Alright, assalamu alaikum. So in this video, we'll be starting off where we left off in the last video, and that is electrolysis of molten ionic compounds. Now before we proceed, let's quickly review what we studied in the previous video so that we have our information and knowledge refreshed. So the first thing that we studied was a definition of what electrolysis actually is. So we studied at that point that electro means electricity and lysis is breakdown. So it is basically the use of electricity to cause breakdown of ionic compounds. Ionic compounds are made of cations and anions, which are held tightly together by electrostatic forces of attraction. So if this is a bond, this bond is basically a strong electrostatic force of attraction. Well, now since electrolysis is the breakdown of ionic compounds using electricity, the purpose and rationale of electrolysis would be to separate the cations from the anions. Cations are positively charged and anions are negatively charged. Therefore, what we want to do in electrolysis is that we want all the cations on one side. If I have this mixture of cations and anions, then what I want is that I want all the cations on one side. Let's say that these are the cations. I'll mention this with C. And I want all the anions on the other side. For this reason, for this purpose, I need a very well directed flow of current. And this flow of current, which will obviously be a source of electricity as well, comes from a DC source, a DC supply. So the first requirement of electrolysis, as we studied in the previous video, was a DC supply, which can be a battery or a cell or a power pack, whatever. And why is that so? I'll just draw a cell here. Okay, I guess I have done a small error. Correct that. Yeah, this is how it will be drawn. And why is this so? The reason is that when we're using a DC supply, the terminals are fixed. That means throughout the reaction, this part of the circuit is going to be the negative electrode, and this part of the cell is going to be the positive electrode, the positive terminal, sorry. And therefore, anything attached to it and any will remain negative throughout the electrolysis, and anything attached to this terminal will remain positively charged throughout the electrolysis reaction. However, this is not the case with a DC supply, with an AC supply, sorry. Why? Because in AC supply, the AC basically stands for alternating current, and as the name implies, there is an alternation per cycle. What happens is that if at one instance this is the negative terminal, then at the next instance this is going to become the positive terminal and this is going to become the negative terminal. At another instance, again, this is going to become the negative terminal, and here we will be having the positive terminal. So we basically have a constant interchange when we are talking about a DC supply, an AC supply. What is the main limitation? The main limitation is that we won't be able to achieve this directionality that gets all the cations on one side and all the anions on the other side. Therefore, an AC supply cannot be used. The second requirement of electrolysis was an electrolyte. And the electrolyte is basically the ionic compound that we want to break into its constituent cations and anions. Now remember this, At the end of electrolysis, we won't be getting cations and anions. Instead, we would actually be getting the elements, the parent elements of the cations and the anions. And we'll see that in this very video, inshallah. Right. Again, coming to the electrolytes. Electrolytes are ionic compounds, and ionic compounds, as we know, they consist of cations and anions tightly held together by electrostatic forces of attraction. Electricity has to be passed through an electrolyte in order for the electrical breakdown into the cations and anions to occur. And for this reason, the electrolyte must be a conductor of electricity, and conduction of electricity only takes place when we have free charges. Uh, in a solid ionic compound, the problem is that the cations and anions are tightly held together by electrostatic forces of attraction, and therefore none of the cations and anions are free to move and hence conduct electricity. Therefore, a solid ionic compound, because of absence of any free charges, cannot conduct electricity. For this reason, we either have to melt that ionic compound, that is, we have to break the electrostatic force of attraction that way in order to make it a conductor, or we have to dissolve it. So an electrolyte is defined as a substance in liquid phase, and liquid phase implies to the molten form as well as the aqueous form of any ionic compound, which conducts electricity on the basis of free charges, free, free ions. Right. Now, since in this video we are talking about molten ionic compounds, so the electrolyte that we'll be taking is any molten ionic compound. For example, sodium chloride. And since I'm taking the molten form, it will be in the liquid state. The electrolysis of aqueous sodium chloride will be covered in the next video, inshallah. The third thing that we need are electrodes. And electrodes are basically rods that ensure the the connection of the electrolyte with the electrode. Sorry, the electrolyte with the power supply. So these are our electrodes. In the previous video, we studied that there are two kinds of electrodes. There are two ways in which we can classify electrodes: the cathodes and the anodes. Sorry, let's come to this again, to the electrodes part again. In the previous video, we studied that there are two parameters on the basis of which we can classify electrodes. The first parameter was the chemical reaction that takes place at that electrode. And on that basis, we named the electrodes as cathode and anode. Cathode was the electrode at which reduction takes place, and anode was the electrode at which oxidation takes place. I also told you that in electrolysis, cathode will be the negative electrode. Why? Because it is connected to the positive terminal of the battery. Because it's connected to the negative terminal of the battery, and hence it's going to attract positive ions, which are cations. Likewise, the anode is the positive electrode, and hence it's going to attract negative ions, that is anions. The second parameter of classification was whether the electrode takes part in the electrolysis itself or not. And on the basis of that, we named electrodes as inert or active. Inert electrodes were those electrodes that don't take part in the reaction themselves, whereas active electrodes are electrodes that do take part in the reaction, in the electrolysis reaction themselves. In this case, we'll be dealing only with inert electrodes. So let's say that we have graphite electrodes here. Right. So what I'll now do is I'll draw an electrolytic cell containing all these components. So the first thing is a DC supply, which is connected to my graphite electrodes, which are dipping into my electrolyte. That is sodium chloride molten. Now we need to remember this, that ionic compounds in their normal states are solids, and these have, as I said before, these have strong electrostatic forces of attraction that maintain their solid lattice structure. In order to have liquid ionic compounds, we have to provide a very high temperature. Talking of sodium chloride only, sodium chloride is a normal common table salt. In order to melt that normal common table salt, we need to achieve a temperature of 801 degrees Celsius, which is an extremely high temperature. For this purpose, if after achieving the liquid, we switch off the source of heat, there will be a very high possibility that sodium chloride would solidify again. Why? Because the surroundings do not have that 801 degrees centigrade temperature, and therefore sodium chloride will solidify very quickly, giving us the solid ionic compound again, which is not a conductor of electricity. For this reason, we constantly have to provide the electrolyte with heat so that its liquid state is maintained. And when we draw our electrolytic cell, we have to show this heating. And it's very simple. What we do is that under our electrolyte, we just draw an arrow. And this arrow tells us that throughout electrolysis, heat is being provided to the electrolyte to maintain its liquid state. Now coming to the reactions that take place. Uh, this is the positive terminal of the battery, and hence this is the positive electrode. This is the negative terminal of the battery, and hence this is the negative electrode. The positive electrode will be attracting the negative ions, that is anions, and hence it is the anode, and the negative electrode will be attracting the positive ions, which are called cations, and hence this electrode is called the cathode. A small reminder, if you are asked to define what the anode is or what the cathode is in your examination, this is not the definition that you will be writing. The definition of anode is the electrode at which oxidation takes place, and the cathode is defined as the electrode at which reduction takes place. Now, let's move to the electrolyte. What happens is that this electrolyte basically is comprising of sodium ions and chloride ions. So if we take a look at this electrolyte without the electrodes, it'll be having sodium ions, chloride ions, sodium ions, chloride ions, some sodium ions here, some chloride ions here. We have a chloride ion here, we have a sodium ion here, so on and so forth. Now, when direct current is passed through this mixture, through this liquid ionic compound, this attracts ions towards it, towards different electrodes. What happens is that all the negative ions start moving towards the positive electrode, that is the anode. Likewise, all the positive ions will start moving towards the cathode. So at the anode, what happens is that chloride ions, in this case, move towards the anode. So chloride ions move towards the anode, and Sodium ions move towards the cathode. Now, if you recall from the previous video, I told you that the electrolysis reaction will always begin at the anode. And the reason for that was that the reaction that takes place at the anode is oxidation. Now, if you recall again from the previous video, I told you that when we are talking about electrolysis and redox in the same chapter, then we'll be referring to the gain or loss of electrons. Therefore, at the anode, oxidation is taking place, and we know that oxidation is loss of electrons. Therefore, what's going to happen is that whichever species move towards the anode, it is going to have obviously excess electrons. That is why it's an anion. An anion is negatively charged because it has excess electrons. So what happens is that the negatively charged ions that have moved towards the anode, they are going to lose their excess electrons. And these excess electrons are then going to travel to the cathode, where they will be gained by the electron deficient cations. So what happens at the anode? Here we go. So Cl ions, the chloride ions, move to the anode, and they are going to lose their electrons, and they are going to form Cl. Why? Because once the electron is lost, we have Cl. However, there are a number of errors in this equation. The first error being that Cl doesn't exist. We have studied in the chapter of halogens that halogens exist as diatomic molecules. Therefore, it is Cl2 and not Cl alone. And now we need to balance the equation on the other side as well. Therefore, we add a 2 here and we add a 2 here. Right. Since we can see this equation involves ionic species as well. Therefore, this is an ionic equation. And we know that if you don't know, then please add this to the information right now that all ionic equations must have state symbols with them. So chloride ions here, they are in the liquid state. Why? Because we are using a molten sample of sodium chloride. Therefore, I write a small L here to indicate that this is basically a liquid. Now, after it has lost its electrons, it's going to transform to chlorine, which is a gas. Therefore, here we have a small g underneath Cl2. Now there's another mistake. If you take a look at your chemistry textbooks, you will not see any chemical equation which has a negative sign. Therefore, this is not the correct way of writing an ionic equation. The electrons lost from one side are basically gained on the other side, produced on the other side. Therefore, instead of writing negative 2e minus here, we are going to write plus 2e minus on this side. And this makes more sense. Why? Because electrons are actually produced at the anode, and these produced electrons are now going to move into the external circuit to be gained by the cathode. So this is our anodic equation. I'll just clear this mess out so that it makes more sense. So once again, the anodic equation. What happened was that chloride ions migrated to the anode, where they lost their electrons as indicated here and formed chlorine gas. Now what happens at the cathode? Positively charged sodium ions move to the cathode. And what happens here is that at the cathode we have electrons from the anode. And alright, positively charged ions are positively charged because they have lesser electrons than the protons. Therefore, they are electron deficient molecules and they want to gain electrons to become elemental again. Therefore, if this is a sodium ion, it is an ion because it has one electron less than the protons it has. So, it is going to gain an electron from the cathode, and where did the electrons come to the cathode from? Yes, from the anode. Here. Right. So it gains an electron and it forms sodium. Right. Again, this is an ionic equation. So we'll write the state symbols as well. The reaction was being carried out at a very high temperature, and we had a liquid specimen. Therefore, we'll have a small L with sodium ions. And at the temperature of the electrolytic cell, of an electrolytic cell having a molten electrolyte, the sodium metal formed will also be a liquid. So here we go. Now we have our anodic equation and we have our cathodic equation. Now we have to write the overall equation. Remember, the equation of the reaction that takes place at the anode and the reaction that takes place at the cathode. These equations are called half equations. And the two half equations are then used to construct an overall equation. How? We'll just see now. Now there's one very important thing to remember about overall equations. If you look at this half equation for the anode, we see that we have a mention to electrons. If we take a look at the cathodic half equation, we see that there is a mention of electrons. The overall equation does not contain electrons. Therefore, we need to devise a method to cancel out the electrons in the anodic and cathodic equations to give an overall equation. For this reason, the main key behind writing an overall equation is first balancing the number of electrons present in the anodic and cathodic equations. So now if we take a look at an anodic equation, we see that there are 2 electrons produced. And if we take a look at our cathodic equation, we see that 1 electron is used. For this reason, we are going to multiply our cathodic equation by 2. So that we have 2Na plus, which is gaining 2 electrons to give 2 sodium atoms. Now what happens is, we can cancel out the electrons from the anodic and cathodic equations. Why? Because this cancellation actually indicates that any electrons produced at the anode have been completely used up by the species reaching the cathode. And therefore, the overall equation becomes 2Cl minus 2Na plus give us Cl2 and 2Na. So the overall equation becomes 2Cl minus, which is in the liquid state, plus 2Na plus, again in the liquid state, gives us Cl2, which is a gas, and 2 atoms of sodium, which is a liquid. So this is our overall equation. Now, one of the most favorite questions one of the most favorite questions of the examiner is asking the observations of an electrolytic cell. Observation basically refers to something that you can see or smell. Obviously, these are very rough tests, so based on the sight and smell, you cannot really tell the identity of the species being formed. So if we take a look at this of this reaction here, the observations will be, firstly, if we take a look at the anode, what will happen is that a gas is being produced at the anode. Chlorine gas is being produced at the anode. And gases manifest themselves as bubbles. So the first observation is that bubbles of a gas observed at the anode. And what's the property of this gas? It's chlorine gas. And from the chapter on identification of gases and ions, we know that chlorine gas bleaches moist litmus paper. So we can say that bubbles of a gas observed at the anode which bleaches moist litmus paper. And what happens at the cathode? Liquid sodium metal is produced at the cathode, and this will manifest itself as a grayish silverish deposit below the cathode. So the second observation is that silvery deposits of a metal observed underneath the cathode. Right. So this is all for electrolysis of sodium chloride. Let's take another example. Now we will be doing the electrolysis of molten lead bromide. So now we have electrolysis of molten lead bromide. PbBr2 is the formula, and in order to indicate that it's molten, I have mentioned this small l here. Now I won't draw the electrolytic cell here, and we'll try to proceed with things directly. So what are the ions that PbBr2 is going to yield? We can see that we have bromide ions, and from the formula we can deduce that Pb will be having a 2 plus charge. And how do we know that there's a 2 plus charge? Because there are two bromide ions. Therefore, there is one negative charge from the first bromide ion. There's another negative charge from the second bromide ion. In order to balance these two negative charges, the bromide ion should be the lead ion should be having a charge of 2 plus. And since it's liquid, both these ions are in the liquid states as well. So now what happens is that the bromide ions are going to move to the to the anode. So what happens at the anode? Bromide ions move to the anode, and they are going to lose electrons and form Br. What are the mistakes? The first mistake, Br is a halogen, and halogens exist as diatomic molecules. Therefore, it has to be Br2, and we need to do the balancing, 2 Br minus and 2 electrons. The second mistake, absence of state symbols. It's liquid here, and bromine at the high temperatures is a gas. Alright, I'll just tell you something here. Bromine at room temperature is a volatile liquid, right? However, I have mentioned gas here. The reason is that the reason is basically that we are carrying this electrolysis out in molten state. And in order to obtain the molten state, the temperature of the electrolytic cell has to be extremely high. And at those extremely high temperatures, bromine cannot exist as a liquid, and therefore it vaporizes to form a gas. And that is the reason why I've written G here and not L, even though bromine is a volatile liquid at room temperature. The third mistake is that no chemical equations have minuses. So loss on one side is basically production on the other side, and therefore we write plus 2E minus here. Now what happens at the cathode is that the positively charged Pb2 plus move to the cathode. And these are liquids. And these are going to gain electrons and form lead metal, which will again be a liquid because of the high temperature of the electrolytic cell. So here we go. Now we have the anodic half equation, we have the cathodic half equation, and therefore we can construct our overall equation. Now this is a very easy overall equation. Why? Because we have the same number of electrons in both the cathodic and the anodic equations, indicating that any electrons produced at the anode were completely used up by the cations that reached the cathode. Therefore, these are cancelled out, and we get our overall equation as 2Br minus plus Pb2 plus, both are liquids, giving us bromine gas and Pb, which is a liquid. So what will be the observations for this reaction? So if we take a look at the half equation, the first thing that we can see is that bromine gas is produced. Bromine gas has a distinct brownish color. So we can say that the first observation is that we can see fumes of a brown gas at the anode. And at the cathode, what we'll see is we'll see deposits of a metal underneath the cathode. Right, so that's all for uh, electrolysis of molten ionic compounds. Now, if you have made it to this part of the video, very well and very good. If you want, you can see the remaining part of the video, but the remaining part of the video basically is intended for chemistry enthusiasts who want to increase their knowledge for the subject. Uh, I personally was extremely inquisitive about this when I was a student of O-level chemistry. I couldn't find my answer at that time. It was just recently that I found my answer to that question. Uh, the question that arose in my mind was that what will happen if we electrolyze, let's say, molten copper sulfate? So things apparently seem to be pretty simple. What happens is that copper sulfate is going to give us basically comprises copper ions and sulfate ions. Now what's going to happen at the anode, at the cathode is pretty simple. Why? Because at the cathode we'll have Cu2 plus ions gaining electrons and forming the copper metal. Simple. But what about the anode? Sulfate ions are going to move at the anode, and what happens at the anode? It's very attractive to think that something like this will happen. This is a very convenient way of thinking about it. However, this is not the case. Why is this not the case? And why am I saying that this equation is incorrect? Remember, this is not part of your syllabus, so if you're not able to understand this, no problem. But it's always nice to enhance your knowledge about certain things. At least I feel that way, and that's why I'm covering this as well. Now let's recall the definition of an anode. Anode is the electrode at which oxidation takes place. And now take a look at sulfur here and take a look at sulfur here. At this point, sulfur has an oxidation state of +6, and here sulfur has an oxidation state of +4, which is definitely a reduction reaction. And reduction cannot take place at the anode. That is exactly how we defined an anode. An anode was the electrode at which oxidation had to take place and not reduction. Therefore, this is not how things are going to take place. Instead, what will happen is that here you go. This is a more plausible explanation of the reaction that's going to occur at the anode. What happens is that the sulfate ions that move to the anode are going to release sulfur trioxide and not sulfur dioxide. Why? See, if you take a look here, sulfate ion, in the sulfate ion, sulfur has an oxidation number of +6, and so is the case in sulfur trioxide. So there is no oxidation taking place here between the sulfurs on both sides of the equation. However, oxidation is taking place because of this part. This part is oxidation. No oxidation, no oxidation on these ends. Therefore, when aqueous, when what do you say? Molten sulfates are electrolyzed, the product at the anode is sulfur trioxide and oxygen gas. Now remember, since this is happening at a very high temperature, what happens is that sulfur trioxide and oxygen react again and they produce something called a pyrosulfate ion. And this pyrosulfate ion is basically S2O7 2 negative ion, which is a bit beyond the scope of not bit this is pretty much beyond the scope of O-level syllabus. But if you are interested in this and if a question like this ever came to your mind, this is the answer. I'll just reiterate this again. If you have a liquid sulfate, then what happens at the anode, at the cathode is pretty simple. Why? Because the cathode is a metal ion and the metal ion is going to gain electrons very simply and form the metal. However, at the anode, the sulfate is not going to form sulfur dioxide and oxygen and give two electrons. Why? Because in the sulfate ion, sulfur has an oxidation number of +6, whereas in sulfur dioxide, sulfur has an oxidation state of +4. That means sulfur is being reduced, and at the anode, reduction cannot take place. Therefore, a more plausible reaction is that the sulfate ion produces sulfur trioxide and oxygen and gives out two electrons. Why is this more plausible? Because in both sulfate and sulfur trioxide, the oxidation number of sulfur is +6. Therefore, there is no oxidation in sulfur between on both sides of the equation. However, this equation is still an oxidation reaction because two electrons are being given off nevertheless. So this is how electrolysis of liquid sulfates takes place. Again, this is not part of your syllabus, so if you do not understand this, no problem at all. If you have any queries, you can ask me in the comment section and I'll try my level best, inshallah, to cater to those queries. We'll be back in the next video, and in that we'll be learning how to electrolyze aqueous solutions. Till then, assalamu alaikum wa rahmatullahi wa barakatuh.